Welding is the process of joining or fusing two pieces of metal by applying heat. It often involves the use of an intermediate or filler metal. From skyscrapers to household appliances, from bridges to the vehicles that use them, the world is made up of patterns of welds. Most types of aircraft construction utilize some form of welding. For the home builder, being able to weld is a definite plus. The basic skills can be understood in a few hours. As with any art, to successfully perfect those skills takes patience and practice. If you've shied away from welded home-built projects in the past, this program will help alleviate some of your concerns. While it's not a substitute for professional instruction, it will teach you the necessary skills to help you take that first step. There are two primary welding families, gas and electric welding. In gas welding, fuel such as acetylene or propane is combined with oxygen, allowing the fuel to burn intensely when ignited. In electric welding, alternating or direct current is used to furnish heat. Several types of electric welding include metal inert gas, also known as MIG welding, tungsten inert gas, TIG welding, sometimes known by its trade name, heliarc, and plasma arc welding. Stick or electric arc welding is not used on home builds, as it burns through the thin metal tubing too easily. For the purposes of the typical home builder, the gas welding type known as oxyacetylene is a common choice. Later in the program, we'll discuss TIG welding, which is rapidly becoming an attractive alternative for some home builders. The basic structure of our presentation is as follows. First, we will cover the various equipment you will need for your own oxyacetylene setup. The main portion of our program will be spent in the actual demonstration of oxyacetylene welding techniques. As previously mentioned, we will also briefly explore TIG welding. Finally, immediately after the credits of this program, we will provide a list of additional services provided through membership in the Experimental Aircraft Association. If you encounter problems in any area of your home build project, technical assistance from EAA is only a telephone call away. Mr. Bill Rohrig is our instructor. Bill is an EAA member and a welder with more than 50 years' experience. Bill is also a vocational school instructor, and he's been doing that for the past 37 years. Bill, for the beginner, how difficult is it to get started?
It's really not all that difficult. There's nothing mysterious about it. Almost anyone can learn the skills if you pay attention to the basic fundamentals. As a matter of fact, if I can do it, I think almost anyone can do it.
Okay. Well, let's begin by familiarizing ourselves with the equipment used in an oxyacetylene setup. The most crucial items are the two gas cylinders, one containing oxygen, the other an acetylene acetone mixture. Each gas is under pressure and therefore must be handled with care. Many welders rent their gas cylinders. Maintenance and replacement is then handled by the supplier. The responsibility of having the tank periodically stress tested is also theirs. On the top of each tank is a valve to which a regulator is attached. A pair of pressure gauges and a hose line are connected to each regulator. One gauge on each tank indicates the pressure inside the cylinder. The other indicates the pressure inside the hose. The hose from the oxygen tank is green. The hose carrying acetylene is red. A longer set of hoses is convenient since it eliminates constant repositioning of the tanks as you maneuver around your project. To prevent transposing the hoses, oxygen hose fittings feature right-handed threads, while acetylene threads are left-handed. The tank should always be secured in a cart or chained to a wall to prevent tipping. A dangerous explosion can occur if the valve of the cylinder is damaged or separated from the tank. When not in use, the valve should be protected by caps. Always keep the bottles in an upright position. Never store cylinders in the trunk of a car for extended periods. After transporting, let the acetylene tank stand for a few hours before use so the acetone can settle. Never draw more than 15 psi from the acetylene tank, as this may cause the liquid acetone, the medium that contains the gas, to be expelled with the acetylene. The acetone is extremely flammable. Other safety tips to remember. Never attempt to repair any part of the setup by yourself or interchange any component with another part. Never scratch or etch any marking onto the tank. Never use oil, gas, or any combustible substance around the welder. Make sure your hands are also free of oil or grease. When these simple precautions are taken and a little common sense is used, welding is a very safe activity. The way the welding apparatus works is easily understood. The gases exit the tanks through the regulator, which steps down the pressure to manageable levels, then out through the hoses to the torch. Inside the torch, the gases combine in a mixing chamber that can be adjusted by two knobs at the end of the torch. The combined gases travel out through the end of the torch tip, where they are ignited. Torch tips come in many sizes. In addition, special cutting torch attachments are also available. The torch itself comes in several styles, including this Dillon MK3 torch from Australia, which works much like a pistol. A flint striker is used to light the torch. Never use a lighter, matches, or any open flame to start a welding torch. Our last component is the filler rod, a piece of mild steel. Do not use coat hangers, as the metal is often impure and can destroy the integrity of the weld. The metal you will be most likely using for your project is chromoly steel, more commonly known as SAE 4130. For practice purposes, however, you want to use something a little less expensive. A word of caution here. Don't just grab any scrap of metal. You'll still want to make sure to use quality pieces of mild steel for practice. SAE 1018 or 1020 are good choices. Pieces as small as 3 inches by 5 inches are acceptable. As with any area of your home building project, you'll want to work as safely and as comfortably as possible. The proper clothing for welding include jeans or work pants and an apron of fire-resistant material, leather work boots, a pair of leather gloves, and eye protection. Goggles come in many styles and are a must. If you wear prescription glasses, you might want to consider a face shield of some sort. Your work area should be well lit and free from drafts that can cause steel to harden and become brittle. You'll also need a workbench and a chair for when you're practicing, and you'll need a jigging setup for when you actually weld on your aircraft. 2 additional items are needed for practice: a pair of pliers to handle hot metal and fire brick to protect your work table. Never use stone, concrete, or regular brick, as they can explode when heated. Throughout the program, we'll periodically show you the weld as you would see it through your welding goggles, because seeing the consistency of the puddle is very important. Bill, what's the first step? Where do we start?
Well, we start by opening the tanks up. It doesn't make any difference which tank you open first, but there is one precaution, and that is to see to it that this T-handle is loose, backed out counterclockwise. If you turn it too far, it'll fall out on the ground, but don't worry about it, put it back. But it must be loose. When you open the oxygen tank, which we're looking at now, you want to make sure that you open it slowly, because if you let a snapping type of surge of gas coming in here, you're liable to either spring the gauge or damage something inside the regulator. We know that we're dealing with perhaps 2,500 pounds pressure on a full tank, so we take that precaution each time. In order to open that tank slowly, I like to grab this valve with one hand, put my other hand on top of it. With this hand, I want to try opening. This one, I want to try not to let it open. The idea being, we do not want it to snap open. Okay? And when I'm doing this, I'm going to look at that very first gauge closest to the tank, and as I break the valve open,
Sure.
I want to leave it come up as slowly as possible. When it reaches maximum, then you open this valve all the way. It happens to be a double-seated valve in here so that you don't lose precious oxygen through the packing gland of the valve. The next step is to get our oxygen into the line. And we do that by tightening up this T handle. And since this is a relatively high reading gauge, we're going to have to guess at about 5 to 7 pounds. And that's more than adequate for what we want to do here.
All right.
So the oxygen is set up, ready to go. And we'll go to the acetylene tank. Now this one has a wrench that you use, and it's fit on a stem down here so that unauthorized people don't end up opening this tank up and filling the room with acetylene. Very dangerous situation. When we open this, again, this precaution of making sure the T-handle is loose is very important. Then you open the wrench a half a turn, and that's all that's necessary so that we do not bleed the acetone into the line. And once we have that done, we turn the T-handle in until we get a reading on the second gauge of 5 to 7 pounds. That setting is not critical, as some people seem to think, because all we're interested in doing is supplying enough pressure to feed the torch.
Are we ready here then? Anything else we need to do in this area?
No other thing at this point. No.
Okay. What's next?
Just light the torch.
Okay.
When we light the torch, you put the torch in the hand that you intend to use. In other words, if you're right-handed, hold it in your right hand.
Sure.
Don't get in the habit of shifting the torch from one side to another, especially after it's lit. And with that thought in mind, you want to adjust the tip by loosening this little nut here to whatever position you are comfortable with. There's no cut and dried way to do that. I like to do it this way, where I have access to these valves. And when you're ready to light the torch, try the scratch lighter to make certain that it is working. Then you can reach over with your other hand, open the acetylene valve slowly, about 1/8 of a turn, and if you see it smoking like that, you know you don't have it on hard enough. So we add more and more acetylene. If, on the other hand, it jumps away from the end like that, it's on too hard. So what we want to do is to get that midpoint between smoking and jumping away. Now you have the starting point for adjusting. The next step is to begin to add our oxygen. And our purpose here is to try to consume both gases completely. And you'll notice as I add the oxygen, the flame changes considerably.
Big difference in the flame, yes.
Yes. At this point, you probably will want to put on your goggles so that you can see the details of this. If you look at this flame, you'll find that you have a long flame out at the end here that's known as the envelope. You have a mid-flame here, and if you look closely, you'll see a bright cone down at the bottom.
I see that, yes.
This one out here, this middle flame, we'll refer to it as the acetylene flame. That indicates that there's more acetylene than there is oxygen in this system. So we're going to add more oxygen to hopefully balance this thing. And as I add more oxygen, you see the flame shortening up until it almost disappears into the bright cone. You stop when you just have a whisker of that acetylene flame showing. I'll bring that back again. There's the acetylene flame, this midpoint. We're going to continue to add oxygen until that just disappears with the exception of a little whisker of it. This then is what we call the neutral flame. Very, very important.
So what would some of the results be of a poorly adjusted flame?
Well, if you had excess acetylene indicated by that middle flame, you're going to contaminate the weld. You'll actually change the chemistry of the metal, and you'll have a poor weld. It will not be smooth, it will be rough looking, and so on. If, on the other hand, you went so far with your adjustment that that middle flame disappeared completely, and you did not have that whisker there, you are then into the range of what we call an oxidizing flame, and that also will ruin the metal.
Okay, what's next, Bill?
Well, obviously we would begin welding at this point, but let's learn how to shut it off.
Okay.
And just like an aircraft, we shut off the fuel first, which is the acetylene, and then finish up by shutting off the oxygen, and we're all set. Well, we'll relight the torch then and proceed with our welding. Remember, we opened that acetylene valve about an eighth of a turn, light it immediately. If it smokes, it's not on hard enough. If it jumps away from the end, it's on too hard. Then we'll add our oxygen as before, remembering that we're shooting for a neutral flame where that middle acetylene flame almost disappears into that bright cone. Be certain that you have a slight whisker of it left. So we have our neutral flame. We're ready to begin our welding. So let's pull our goggles down now so that we can see this. And we're going to go right to the workpiece. Do not sneak up on it. And hold that flame about a 1/16 to an 1/8 of an inch away from the surface. In about 10 seconds, you'll see the puddle forming. In this case, there's a slight little scum on the top, which will be normal. And once that puddle forms, we want to ease ahead with the flame, carrying the puddle along with us. This action is known as running a bead. And as we do this, you'll notice that the flame is pointed slightly in the direction that we're traveling. This is important that you do not go too much on that one. In other words, don't point the flame too much forward or you're liable to preheat too much of the metal.
So what about reading a puddle?
Reading a puddle means to look at the top of the puddle as you see it here, knowing from the reading of it or the way it looks that you have penetrated properly. After all, when you are welding tubing, there's no way you can get to the backside of that weld to see whether it's penetrating. You have to know that from the top. So in reading the puddle, you want to see the puddle sag and sink in as you're moving along.
How important is rate of travel at that point?
Rate of travel determines how wide the resulting bead will be. For example, if I move too rapidly, you end up with surface melting and a very narrow-looking affair, and that is not what you want. If you move too slowly, and I'll attempt to show that here. If I go too slowly, you're going to find that happening. And you see that you have a hole melted right in.
Yeah.
Don't be alarmed if you see yourself burning holes in occasionally. I'd rather much see you do that than to end up with a little narrow bead that does not indicate good penetration. This exercise is designed to help you gain a little confidence in yourself, knowing more about what will happen to the metal as you heat it up and as you melt it.
When choosing a torch tip, keep these rules of thumb in mind. If it takes longer than 10 seconds to create a weld puddle, first increase the flow of both gases. If the torch begins to hiss, you may need a larger tip. If the steel melts faster than you can control, first reduce the flow of gases to a smaller neutral flame. If the tip begins to pop, signaling too little gas flow, you may need a smaller tip.
Our next exercise is to run the same sort of a bead that we had done previously, excepting this time we're going to add rod to it. And in so doing, you go right down to your spot that you wish to weld. You generate the puddle, keep the rod in close, and when the puddle forms and the rod has a little droplet at the end of it, you dab it into the center of the puddle. Now, it appears as though there's a rhythm involved there, and in reality, I'm simply looking at the puddle, making sure that it's the same size all the time. I lift the rod up from time to time in order to preheat ahead of the bead so that we're sure we have a good deep melt on it. This is the key to it. This particular exercise is the one that you ought to spend the most time practicing because it will pay off in the long run.
So what do we need to look for at this point now?
Well, what we're looking for is some of the same features we saw earlier. Namely, we want to make sure that that bead is uniform in width, has uniform ripples on it, has a crown on it, and is shiny. The shininess indicates that you've done the proper things with your torch adjustment and everything else. The next thing we want to do after you have gained confidence in running the bead with the rod is to weld two pieces together bead, but this time over the joint between two pieces of metal. The purpose, of course, is to show you what welding really is all about, namely joining two pieces together. But in order to do this, we're going to have to first tack this end, and after a while we'll tack this end as well. So we'll need to tack this end first, which means that we're going to weld them together with a small weld. Tacking seems to imply something very small. In reality, it's best if it's a little larger. And the way to handle that is to simply go right on down with your torch and the rod and melt some of the rod directly onto the point that you wish to tack. And if we take a look at that, we find that that globule of metal was molten and a different color than the rest of it, which meant that it was not melted in there, although it's sticking there. So in order to achieve that, we'll get right down with the torch, remelt that globule, and when it spreads out, as you see it right there, we now have a very, very solid tack, indicating that you will not find your pieces falling apart when you take them out of the jig. So the next step then is to come back to the other end, do the same thing, put a droplet of metal on there, and when it all becomes one color and flows out like you see that, you have your puddle established. And we simply carry on as we did before, adding rod in much the same manner, but this time doing so right over the top of the joint of the two pieces that we're welding.
So it looks like we've got a good weld there, but how do you test it?
Well, first of all, looking at the puddle as you're welding will tell you you've got proper penetration. If the weld looks good and is shiny on the surface, as we pointed out before, chances are things are pretty good. But in your own mind, you may want to know, well, how strong is that? And for that reason, I would suggest that you test it by putting it in a vise, bending it, hammering it, stomping on it, whatever you feel you want to try, to give you the confidence that welding is a very good way to go.
Fitting the steel tubing of your airplane is one of the most important and time-consuming jobs on your home-built project.
Once you have mastered the art of running a bead using rod to fill up that bead, you then are ready to apply that skill to welding two tubing pieces together. And we'll be running that bead right up this joint right here. But before you do that, you have to shape the tube to fit this curve. And in order to do that, you may want to use a hacksaw to saw that off to generate that curve. Or you may want to use a tin snip to do likewise, and then finish it off with a rat tail file to get a more precise fit.
So suppose I'm not handy with a hacksaw or a tin snip, what are my other options? What else could I use?
Well, you could always use a grinding wheel that is shaped to roughly this curve and simply grind those shapes in there. Or you can buy a commercial unit that mounts in a drill press and will cut those things very accurately for you. Once you have the pieces cut and fit the way you want them, we're going to have to tack them together at this point and on the opposite side. And I'll demonstrate that for you so you know exactly how to do that. Now, in our case, where we are making practice welds, we're going to weld this up immediately after we tack it. When you're building an aircraft, that is not the way you do that. You tack the whole fuselage or the item together and then take it out of the jig, and then you do your welding. But for practice purposes, this is the way we'll do that. So we've got everything set up here now, and we'll proceed to do our welding. You'll need your goggles on in order to see this. And I'll get my gloves on, and we'll light this torch, again making sure we have a neutral flame. And remember the smoking, there's no smoke. Add our oxygen and achieve the neutral flame. Now, since we've got a little larger piece here, I'm going to increase the flow of both gases, which is entirely legal. And our first step then is to tack this together across here. Now, as you recall, when we tacked the plates together, I put a globule of metal there, melted it in, and then left it. In this case, I'm going to go a little bit beyond that. I'm going to run a small little bead across there. And the reason for doing that is so that you're sure this thing is not going to fall apart for you when you take it out of the jig. Now, since this piece that I'm on now, the longer of the two pieces, will take a little more heat to bring it up to melting temperature, we preheat it slightly, as you see me doing now. And when it comes up to a dull glow red, then we're ready to do our tacking. If we didn't do that, that raw edge of this piece would probably melt away before the other one even melted. There we see it flowing out. And now I'm just running a little short bead across the top. The reason for that is to give you a very secure tack, and at the same time, it's going to provide us with a heat sink that we'll be utilizing later on. Now, here we are, we're tacking the back side of this. Get a globule of metal in there. We allow it to melt into both pieces well, and then we run a little short bead across the top. And then we're going to simply go down in this corner here, and you'll notice the position of the flame is horizontal to the tubing itself. And we're now going to put a droplet of metal or globule there, and then we're going to concentrate heat on that until you see it melt in deeply. And once it has, then we're simply going to add rod and run a little bead up over the top. Watch my torch as we get near the top. It rotates around so that we're pointing directly at the puddle. When you get to the top, where all that heat is accumulating, that's where that little bead comes in. That has absorbed some of the heat, helping us to control it. Then you come over to the other side, and you do exactly the same thing. You get a globule of metal down at the midpoint, with your flame pointed horizontally. And when you've got a good portion of metal down there, you melt it in deeply, and then start adding rod rapidly as you come up over the top. You may have to change position from time to time, but that's normal. And once again, where you get up at the top here, where you have a lot of accumulation of heat, that little short bead you put in there will stand you in good stead. You maybe noticed when I finished the weld that I took the torch and backed it off at a little circle like that. That is to prevent a hole forming in the center of the crater.
We tested the other weld on the 5 metal earlier. Do we test this?
Well, remember that was a destructive test. If you're building an aircraft fuselage, obviously you cannot test it other than with X-ray, but if it's a practice weld, you may want to saw that apart with a hacksaw and look at that joint. And if everything looks fine to you, you're satisfied that you've learned what you need to learn. Now here again, you should see a relatively smooth weld, uniform ripples, and filling in a nice fillet in the corners. When you're through with that, you simply turn it over, and we're going to do the same thing on this other side, but rather than put a droplet or globule of metal as a starting point, we already have that there from our previous weld. So what we'll want to do is to heat that up well. Always check your neutral flame. You might bump the handle sometimes. And you get in here and you melt that previous metal until it forms a nice, deeply melted puddle. And once that forms, and you simply start adding rod to it and proceed with your bead right up over the top. Always keep your eye on that puddle. Rotate the torch so that you're pointing directly at the puddle. And when you reach your tack, carry right on into it. And do likewise with the final side here. Once again, making sure the original weld has melted thoroughly into the two pieces of tubing. When that happens, then you begin to add rod and run the bead right up through the joint. Always keeping an eye on the puddle so that it's the same size and you end up with a nice uniform bead. When you get to the top, you carry on in the same fashion, and when you're ready to quit, you back the torch off slowly so that the crater does not form that hole for you. And that then constitutes a weld of two tubes together. And in so doing, you have learned the fundamentals of joining the cluster, which is really nothing more than adapting this very same technique to more than two tubes. Here in this case, we have three of them joined to what would commonly be known as a longeron. The welding procedure is the same. You start at the center or the bottom, or middle edge here, and you come up. You do likewise on all of them. You can alternate from side to side or whatever way you want. Some people like to alternate in quarters like that. And once you have finished welding that tubing all together on all sides, then we do what we call stress relieving and normalizing. They're more or less one and the same thing. And what you'll be doing is heating this whole area up, welds and all, until they're a very definite, uniform, bright red heat. Be sure the torch is constantly moving, because at that temperature, you're apt to burn a hole in there if you stop. And when the whole joint is completely red, then take the torch away and let still air cool it down. And I can show you how to normalize this on this particular practice piece. You probably will need a larger tip in order to heat that up sufficiently. As I said before, you must always keep that torch moving, and we're going to heat so that the heat will be about a half to a whole inch away from the weld itself in this whole area. If it's a fuselage that you are heating up, you'd be getting at both sides of this. We'll see if we can do that from one side. We're coming up to heat now. You can see quite a little red glowing all over the place, but it still is a long way from being what we want. As you heat this, you will notice that the weld itself will not come up to temperature or the same color as rapidly as the rest of it. That's normal because you got a little extra metal in there. And that's the way the joint should look for normalizing on both sides. You will have relieved a great deal of the stress, taken out some of the warpage that naturally will occur, and you're ready to remove the thing from the jig and put it into use elsewise.
Next you're going to show us how to lap weld. Before you show us that technique, where would we have occasion to need to use a lap weld?
Well, generally, wherever you are in a restoration project, it becomes necessary to replace pieces of tubing, and you need to reinforce them by inserting another tube on the inside. And the resulting joint, and that's cut off at an angle as specified in Part 43, and various other shapes, constitutes a lap weld, where you have two different heights of metal.
Sure.
Another variation of a lap weld is what is known as a rosette weld. We have drilled a hole previously into the top tubing, and then we're going to lap weld it to the bottom. Now we've drilled another small hole in the bottom tubing to help facilitate the melting of that inside tube. So before you get into that, however, it's best to practice with pieces similar that we used earlier.
Okay.
And in order to simulate a lap weld, we simply place one piece over the other, as the name implies, lapping it together.
All right.
And from that point on, we're going to tack the pieces so they don't move out of position. As before, when we tack, we're going to place a globule of molten metal in position at the far end of the weld, assuming we're going to weld in this direction. And in doing so, we get right down here and melt our globule of metal on there. And as we keep on heating that globule up, it will eventually melt into both of the pieces, tacking it or welding it together at that point. Be sure you have a nice, deeply melted tack. We'll come over here to the opposite end and do likewise. Put our globule of metal on there. And again, keep heating that until you see it melting into both pieces. When it is done so, the next step is to preheat the bottom piece, because that's going to require a little more heat than the top one, since there's no exposed edge there. In preheating it, you help yourself as you move along here. Now, we create the puddle again, right where the tack was, and once the puddle is formed, we simply move along exactly the way you did before, seeing to it that the puddle engulfs the upper edge. And that constitutes a lap weld. All right, when you finish this weld, you ought to expect to see roughly the same thing you saw with regular beads, normally a uniform width, uniform ripples, and a shiny surface. That indicates that you had things correct. Now, there are times when people worry about this undercutting or cutting into the top piece, as you see here. When that happens, you simply move your rod over there and fill it up and continue on. But keep the bead running in the same line.
How do we do a rosette, Bill?
Well, a rosette weld, as I said before, has to do with welding a lap weld around a hole so that you can join the bottom and the top piece together. Now, we've drilled a hole in that bottom piece to help it melt quickly enough to do what we want to do. This is a rather rapid thing happening here. Now, as we create this puddle and a lap weld, we simply go right around that circle, welding the bottom edge to the top edge. And you're really doing nothing more than running a bead in a circle instead of a straight line. And when you get it all done, and back it off in the same fashion, and you have a rosette weld.
And the hole disappears.
The hole disappears, that's correct. Well, as long as we are talking lap welds and so forth, let's go ahead and weld up a splice joint. This is very common, as we pointed out a minute ago. I've already tacked that together, and the procedure is much like it is with welding a 90-degree rod or tubing onto another tube, in that we start down here and come up 1/4 of the way, flip it over, touch the other quarter, and work our way around. I'll go for 1/4 of the way to demonstrate the process. We'll leave it at that.
Okay.
So we get down here. We get our globule of metal in there just as we did before, remembering now that we're making a lap weld up here, and we just roll right up over the top, making sure that you've got a good, deeply melted puddle. And the procedure from that point on would be to carry on with the other quarters, and you have completed the splice joint at that point.
So what type of weld is this?
Well, this is going to be a fillet weld, where we weld a vertical piece to a horizontal piece. Now, that is frequently used in aircraft work and construction, wherever we need to mount a pulley for, let's say, a control cable or things of that nature. And so, in order to make that weld, I've already tacked two pieces together, and we'll light the torch and proceed to make a bead in that corner in much the same manner as we have when we were practicing running a bead with a rod on flat work. The only difference here is that we're going to angle the flame, approximately splitting the angle between the two pieces, or at about a 45. We create a puddle in much the same manner, and then we simply move along.
You call it a fillet weld build. As we look at it upside down, of course, it looks like a T, inverted.
Well, it is sometimes known as a T-weld. The tendency for most beginners is to think, well, that metal is going to run down and not take care of the upper part of the weld. So if you keep your rod in the upper part, it tends to keep it a little bit cooler, and thereby keeping the metal where you want it. When you're finished with this weld, it should be, just as the fillet name implies, a 45-degree angle or filling up of that corner. This then constitutes the fillet weld. And this pretty much completes the type of welds that you normally will find in aircraft welding. And the more you practice them, of course, the better your final project is when you look.
You've shown us various types of welds today, and again, the key is practice.
That's right. That's absolutely right.
Okay, Bill, thanks for your help. All right. An increasingly popular form of welding is TIG welding. Let's take a look at that now. The building behind me is the Kermit Weeks Flight Research Center. This complex, which is separate from EAA's museum, is where most of the maintenance is done on EAA's collection of airplanes and jets, including this 1929 Travel Air. This facility is equipped with both gas and TIG electrical welding. Let's go inside. This is Gerard Putzer. Gerard's been a welder at EAA for 5 years. Gerard's going to briefly take us through the TIG welding process. Gerard, before you show us TIG, why don't you explain the differences between oxyacetylene welding and TIG?
Okay, in TIG welding, as a heat source, we use an electric arc created from a tungsten electrode to a ground plane. You can see we have a ground hookup here. Also, you notice on the torch head itself, we have a ceramic cup. Around the ceramic cup, we use a flow of argon to help clean the weld as we go.
Okay. What would we use TIG welding for?
The TIG can be used for a variety of metals, such as stainless steel that would be used on, like, say, aircraft exhaust systems, to mild steel used on many fuselage components, and even aluminum as well, much cowling and oil tanks, fuel tanks are generally constructed with.
Sure. At the oxy-acetylene welding setup, we were standing. Of course, here we're sitting. How come?
Well, it's a little bit more comfortable to sit, and also you may have noticed that I'm using a foot pedal here. That does two things for me. I'm selected in a remote contactor mode. It enables me to turn on power to the electricity at the precise moment that I want it. Also, it helps me I'm able to vary the currents as I'm going along, pulling higher currents to initially start the weld and then backing off once I have a puddle established.
Well, you look comfortable. Why don't you show us how to do it?
Okay, if you want to put your helmet on, we're all set here.
What do we need to look for on this weld now, Gerard?
Okay, basically you can see that it's very, very quick. The electric arc produces heat rather fast, and unlike conventional stick welding, we don't have a slag. The argon helps clean the weld as we go.
Looks good. Gerard, thanks for your help on TIG welding.
You're welcome.
As you've seen, welding is a challenging but worthwhile extension of your home building skills. Whether you use gas or electric welding methods, it requires practice to get it right. Don't become discouraged. Practice with scraps before attempting to weld an airframe. And before you know it, this tubing will become one of these.
For more information on joining the Experimental Aircraft Association, call 1-800-843-3612. Membership in EAA includes a subscription to Sport Aviation magazine, access to trained technical counselors as you proceed on your home build project, a voice in Washington in sport aviation-related issues, the opportunity to purchase aviation videos and books, such as the Tony Bengalis 3-volume Sport Plane Builders Library, and there's much more. For more information on the Experimental Aircraft Association, call 1-800-843-3612.